So this is the last slide that where we had ended yesterday, last lecture, that how the predicted changes in bone density for different designs of the hip resurfacing implant can be sort of predicted by the simulation. And all these results that what we what I am showing you in detail is has been produced in the laboratory, and these results do have clinical relevance, and accordingly these are published in top journals. So you can see a more detailed results in the publication as I have indicated below. Okay. Now we had also performed experimental investigations, basically to validate the results that are predicted by computer simulation. And basically you can see that this is performed on a synthetic bone, an artificial bone. So this is a sample that can be obtained from Sawbones, Sweden, and we had actually implanted it with a resurfaced implant. You can see here. It's a cemented variety, so you can see the cement sticking out, the white part. Okay. And then we had also put strain gauges on the proximal part of the femur. And we have also tried to measure using LVDT, linear variable displacement transducers. So we have tried to measure displacement along orthogonal directions, okay, of the implant with respect to the bone. Okay. Plus, we have also, you can see an LVDT3, which is, trying to measure the displacement of the tip of the implant. If I try to go back, so here, yes. So we have tried to measure the tip of the implant, how it is moving inside the ringed hole. Okay. So this is the LVDT3 that measures the movement of the tip of the stem. Now this was designed in our laboratory. It's still there in the laboratory, but unfortunately I could not show you. This is a load application mechanism designed and fabricated here. So it tries to mimic the loads, the biaxial or triaxial type of loading that actually is present in case of a natural knee joint. Okay, so it has roller tapered bearings and things like that. So when we apply a load from above, it also takes into account the displacement of the acetabulum with respect to the femur. Okay, so this is also published in Journal of Biomechanics. So you can see the implanted composite femur mounted with strain gauges and LVDTs on a mechanical testing machine. Okay, so if I give a load, and then we can measure displacements in LVDT1, LVDT2, LVDT3, as well as the strains. We can do it for before implantation, we can do it after implantation. So it's a major experimental investigation to validate the numerical results. So the next important work that was done was focused on the pelvic bone and optimal design considerations for uncemented acetabular prosthesis. So you can see here a little bit background of why we did this work. So we had explained to you earlier the structure of the pelvic bone. You can see here. This is the acetabulum. This is a sort of side view. Now the clinical feedback studies reported that acetabular component loosening, so mechanical loosening of the acetabular component, was found to be 2 to 3 times higher than that of femoral components. So acetabular component fails at a much higher rate than the femoral component. And one of the major causes behind this aseptic loosening, note the word aseptic, okay? Aseptic means non-septic, okay? So failure of the implant, which is purely due to mechanical causes, not due to infection. The word septic comes from infection. It's not infection-related loosening or failure, but it is non-septic or aseptic loosening caused due to mechanical factors. Okay. Now, of course, the demand for more and more durable implants are increasing because more and more younger and active patients undergo replacements due to various reasons. And we also have the increase in life expectancy also for older patients. So the implant design and manufacturing both is undergoing evolution. So there is evolutionary changes in different kinds of implants that are coming into the market, and the durability of the implant, mainly in terms of life expectancy and since more younger and active patients undergo replacements, better and better implants are required to serve the purposes. So here also we actually do the same procedure. So we start with the CT scan, then thresholding, region growing, and contour detection. So once we have the contour, we stack it up for the pelvic bone, reconstruction of the pelvic bone, and then we actually have a surface fitted to these contours, and we have a solid model of the pelvic bone, which is subsequently meshed to form finite element model. Okay, so from image processing of CT scan data slices, as I have already discussed, that we can actually find out for each element the apparent density based on CT gray value, the pixel gray value. We can relate it to apparent density using linear calibration. And as I told you, this depends on the highest point and the lowest point. So lowest point is, of course, HU0 for row 0 for HU0. Okay, so apparent density is 0, close to 0, of course. So if you put a value, rho would become 0.022. So we just don't make it purely 0. It's close to 0. There may be some, sort of material like fat or something, that may be close to 0. But basically, the first point is the 0, point, and the last point is important here. It is the highest AQ value, Hounsfield value, or CT gray value in Hounsfield unit of the cortical bone. Okay, the maximum value. So between these two, we can fit a line. So we do a linear calibration and find out anything in between that range. So once we have the apparent density, we can get the elastic modulus using specific power law equations. So note here that the exponent of rho is 2.46, and this is the relation mostly used for pelvic bone. Okay, for spine you can get another relationship. For femur we used another relationship. So this is all mentioned in your Myomic Doc 1, Doc 2 document. Okay, there are relationships which are region specific or bone specific. But generally, we assume cortical bone density to be sort of 1.73 to 1.75, any value you can assume. But E modulus is about 17 gigapascal for the cortical bone. So the finite element model of the bone, when we meshed it, it had no specific property of the element. But now the finite element model, we can actually map each element, the centroid and the volume of the element can be mapped back to the CT scan data, and then all the pixel gray value contained in that volume can be averaged. So obviously, the smaller the size of the element, the better would be your approximation. So a small size finite element can actually have the averaging effect of variation in gray value would be much less for a small element. And then once we have the average value of the CT gray pixel CT gray value, basically we can find out the apparent density and the elastic modulus, and we can assign that element with individual material properties. So finite element model, where each bone element is assigned individual material properties based on CT gray value. Now we have, for this model, we have about 222,000 number of elements. Okay. Now here also we performed an extensive experimental validation study, but here we not only used strain gauges, we used a DIC, digital image correlation technique of measurement. Now in digital, I am not sure whether you know the principle of digital image correlation. Are you aware? Just a moment. Are you aware of digital image correlation technique?
No, sir.
No, sir.
You have not done it in the lab, right? Mechanical?
No, sir.
Mr. Vemkabam Teja. Okay. Can you hear me?
Yes, sir.
Okay. I will give you the link of my GAN lecture on this. Right?
Yes, sir.
So if you want to rewind and see it again and again, it is not a problem. First, now listen to the lecture as far as possible.
Okay, sir.
Now, digital image correlation. Can everybody hear me?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
I'll better go back to the to presentation mode. Oops. Yeah. Now, digital image correlation is a more full field technique. So it actually, what it does is on a surface, it applies a white paint. On the white paint, it a randomized speckle pattern with black speckles can be sprayed on the surface. Now, what is done is, this is a technique which is non-invasive, so it is camera-based technique. So there are, for 3D measurement, we use 2 cameras, as you can see here. Okay, we track, basically the cameras track the displacement of these speckle patterns. So before loading, it records one area, the speckle patterns, and then after loading, these speckle patterns displaces due to the applied loads on the surface of the bone or whatever material you can use. It is very frequently used also in aerospace structures. Okay, and then we can actually have in this area, black bounded area, you can see it is enlarged. We can have the displacement field across this area. So it is more a full field technique rather than a discrete value at a particular point, which was mostly available with the strain gauge technique. I hope you all know about strain gauge technique. Hello?
Yes, sir.
Are you aware of the strain gauge technique? Okay.
Yes. Yes.
Now, what strain gauge does is, because you have already seen that we had glued strain gauges on the bone surface or anywhere on any surface. It gives you a local data. Okay, underneath the gauge. Okay. Now, if there is a sharp gradient, stress gradient or strain gradient in that region, it is quite obvious that this sharp gradient may not be captured in the displacement data record strain recorded by the gauge. In comparison, the full field, this digital image correlation technique gives you a distribution of displacement, strain, stress in an area rather than a point. Okay, so it gives you much more information and it is more a full field technique. Okay, wherein you get a complete distribution. As I show you the results, you will clearly understand it. Okay, so let me get back to the So if anybody is interested, you can just go through it, not read it line by line, but you can easily understand once I present these results. So here you can see that the pelvic bone also is, we use strain rosettes on the surface of the bone, and a system of linear displacement sensors, LDS 1, 2, 3, which were mutually perpendicular, mutually orthogonal. Okay, so LDS 1, LDS 2, and LDS 3 records displacement of acetabular implant along 3 principal directions. Okay, plus we have the strain rosettes. And obviously, we tried to generate the equivalent finite element model to get an idea of the degree of correlation between the predicted result and the actually measured result. Okay? Now sorry. Now, if you now look at the strain distribution, equivalent one basis, in the intact and implanted hemipelvis. Okay. On the left, you have the DIC measured. You can see this is the area of interest. Okay, the white bounded area of interest. All values within this bounded white line is of relevance. Okay, so you have the DIC measured for intact pelvis and DIC measured for the implanted pelvis. You can easily notice that the effect of strain shielding straight away. Don't look at the right hand side. Try to look only at the DIC images top and bottom. Oops. Pointer option. Yeah. So this is, I'm now using the pointer. You can see the white line, the boundary. Within this, all data are important and relevant. This is intact pelvis. This is the implanted pelvis. And immediately you can see this effect of stress shielding or strain shielding evident due to huge change in the strain distribution after implantation. Okay. Now let us focus on the right hand pictures. These are figures coming out of FE analysis. So this is FE predicted strain. Okay. If we try to compare, we have to identify the area bounded by the white line in the case of the FE model predictions. So you can see very, very similar type of predictions with actual measurements. So this is intact, this is implanted. Now we can actually compare values also. Now if we try to correlate DIC measurements with FE predicted strains, on x-axis FE strains, microstrain, on the y-axis measured strain from DIC, you can actually plot a host of data, and if you conduct a statistical analysis, we actually got very good correlation coefficient of 0.956 and standard error of about 70 microstrain, which is negligibly small considering highest strain measurement of about 1200 microstrain. Okay. This is for the intact case. On the right, we have for the implanted case. Slightly lower correlation coefficient, a little slightly higher standard error, but still it gives you very good correlation between FE predictions and actual measurements. Now, if you use strain rosettes, here also we can see that it is highly correlated. Okay. Results of this is not DIC. Please note that this is strain rosette measurement. The same bone, intact as well as implanted. First, we performed the DIC measurement. Then we had, erased the paint, and then we put the strain rosettes, and we had this results. So it is a two-way validation. The FE predicted strains can be compared with DIC measurement. It can be also compared independently with strain rosette or strain gauge measurements. Okay, so from both sides, we can conclude that the FE strains are valid predictor of the actually measured strains in the pelvic bone. Just a moment. So in this case, you can see the correlation coefficient even higher for the strain gauge measurement and if we predicted strains. R is equal to 0.974 for the intact pelvis. For the implanted pelvis, slightly lower, 0.973. But overall, very good correlation. If we are comparing the LDS measurements, linear displacement sensor, remember this is an uncemented prosthesis, uncemented acetabular implant. So it is press fitted within the acetabular cavity. And obviously, there would be some relative displacement between the implant and the bone, which can be measured using this LDS. So in biomechanics, we call sometimes implant bone relative displacement as micromotions. Okay, micromotions term comes generally means relative displacement between two bodies. Okay, so we can actually measure LDS1, LDS2, and LDS3. So one is FE predicted, another is measured, and this also actually shows very good agreement between the two predicted, between the predicted data and the measured data. So all are published in good journals in the area. So once we are convinced about the quality of the finite element model that is being used for clinical investigations, we refer to the musculoskeletal data, which are used as an applied loading conditions. Okay, so we had shown you this slide, I think, earlier in case of mechanical behavior of bone. So we have the pelvic bone and we have the femur bone here. And we actually also try to model very intricately the cartilage layer in between. Okay, we directly don't apply a concentrated load directly on the acetabular surface. We applied it at the center of the femoral head. And then when we have this cartilage layer, if the cartilage layer is obviously present in case of a natural bone, so let the structure distribute through the cartilage what will be the amount of, how will be the load distributed in the acetabular region. So it is better to mimic the natural situation because the structure will have impact on the load distribution or load transfer across the acetabulum. So we have made a detailed model of the cartilage, the femoral head, as well as the acetabulum. And then we applied the hip joint contact force at the center of the femoral head. But in this analysis, we are not interested about stresses within the femoral head. Okay, that is only used to transfer the load from the femur or between the interaction between femur and the pelvic bone. It is only used for load transfer, nothing else. So this is basically the distribution of joint reaction force with respect to the percentage of gate cycle. Okay, so you all know about this on the left hand side as I show you with my pointer. Now, this is results where principal stress distribution across the hemipelvis. I'm showing you only the results corresponding to load case 2, beginning right single support phase, where we have the maximum hip joint reaction force. So this is the first principal stress distribution in the pelvic bone, intact pelvic bone. Both views, both sides. And the third principle, stress distribution. So we can have anything and everything once we have the analysis done, and you can believe in the results of the model predicted by. So this is realistic level of stresses during a walking cycle. You can have multiple load cases representing a walking cycle. You can have 8 load cases, you can have 10, 12, how many subdivision you would like to do. You can actually simulate that and get hold of the results. Now this I have also explained you earlier that we have the acetabular component next implanted on the same bone. Okay, so in case of acetabular component, a part of the bone, acetabulum will be reamed and the acetabular component placed according to the surgical techniques. So we will use the cut boundaries, the submodeling technique, and I have explained to you earlier how we can compare the results between the submodel and the full model. And as you can see, the submodel actually gives you excellent results as compared to the full model, which is of course a coarser model as compared to the submodel. Submodel is a fine model where we can capture the description of the material properties much better than the coarser full-scale model of the pelvic bone. However, the elastic property of the remaining part of the pelvis, which is not included in the submodel, can be included when we transfer the nodal displacements at the cut boundaries from the full model. Now this is, I also explained to you earlier, changes in bone density distribution in metallic and ceramic implant. Although it is repetition of slides, but it is relevant for this lecture as well. So immediate post-operative, you can see here bone density distribution, with a bonded implant bone interface. Remember, this is all uncemented prosthesis for the pelvic acetabular replacement. For different implant bone interface condition, we have different predictions of bone resorption. Similar, we can investigate different designs and having different thicknesses, different designs. You can see here the cutout, thicker design, thinner design, as well as with cutout, without cutout. So everything can be explored. This is Cambridge cup, this is Mitch cup, Cambridge cup. This is also explained to you earlier. A thicker implant with a higher stiffness. This is a thinner implant, Mitch cup, the lower stiffness. And both these Cambridge cup and Mitch cup both has cutouts following the natural acetabulum. But we also had earlier hemispherical cup without cutout. So obviously, when there is no cutout, the stiffness of the implant increases. And this is repeat results, but you can see very clearly that due to bone remodeling, how the density distribution changes from one design to the other. This is also something I had explained you earlier in the class. Mechanical behavior of bone. As you go on increasing the thickness of the implant, so thick, 3 millimeter thick implant and the 11 millimeter thick acetabular component will have different amounts of bone resorption or bone remodeling patterns. Okay, this is clearly visible in sectional blocks. So this is some of the findings, major findings related to acetabular component replacement. So strain shielding was observed in the central part of the acetabulum, whereas pronounced strain increase was observed around the periphery. I had also explained this earlier during the other topic, mechanical behavior of bone. Strain shielding was considerably higher for the bonded implant bone interface condition. So this I will separately explain you, bonded and debonded implant bone interface conditions. Horseshoe CFR peak appears to be better suited alternative bearing surface other than designs with regard to strain shielding, bone deformation, and bone remodeling. So the Mitch cup appears to be the best within these three designs. And obviously, the thickness of the acetabular component played a crucial role in implant-induced bone adaptation. Remember, this the implant-induced bone adaptation. So here it is purely implant-induced. That once you put the implant, the mechanical environment actually changes. Now, I would stop here a little bit. Any questions? Any questions? Can you hear me?
Yes, sir.
So is it clear? Does it give you a good idea of how powerful these simulations can be if performed correctly?
Yes.
Okay. So let me move on with the lecture.
Sir, I have a question. So
Yeah.
when we are comparing the results and where we said the actual, where we compare the actual results and the implanted results. So
no, actual, no, wait. Actual means measurement. Okay. And
okay, sir.
One is FE predicted, another is measured. Okay. So
yes,
we are actually developing the FE model of the same condition, that on same condition when same condition as prevalent in the experiment. So it is not. It is the bone used for the experiment, and the boundary conditions and the loading condition that has been applied for the experiment is exactly replicated in the FE model. Then only we can actually have one-to-one comparison.
Yes, right.
You get my point. So when we are validating something, we must bring them together at the same platform. Otherwise, you are comparing apple with mango. You can compare apple with apple, right?
Right, sir.
So the experimental conditions, loading, boundary, geometry, everything has to be exactly the same in case of the FE model. Then only you can compare. And that is what is validation. That you try to validate a a result means you validate a phenomenon. This would be the behavior that we are predicting, but when we are validating it with an experiment that proves that the predicted results are actually the realistic representation of the actual behavior of that bone. Okay?
Yes, sir.
Now, remember one thing, in today's world, we do a lot of simulations. A lot of simulations. But all simulations need verification and validation. Because at the end of the day, computer models are models. We can put some garbage in, we can get some garbage out of a computer, isn't it? Although everybody, you know, for all of us, it's a holy machine. But at the end of the day, you have to always question the results of the computer simulation, coming out of the computer simulation. And therefore, you have to prove that your results are correct. And when it comes to clinical relevance, even without looking at the results, the first question that a reviewer poses to a scientific paper is, are your results valid? This is everywhere. This is not only in biomechanics case. This is in any research field you go, be it solid mechanics, fluid mechanics, related to those, where we use a rigorous computational analysis or simulations. You have to remember, you have to find a way to validate and verify, verification and validation of the models used. This is an important step towards proving that the predicted results are correct. Okay? Now let me move on with the, you had any other question, Shivanshu?
In that comparison that we are making, so
Yeah.
I was just curious that whether we did that one experimental data that we are showcasing. So did we do it on the actual bone and or the just the model that you made?
No. We did it on an actual bone, but it was a replica. It is it is a composite bone which is used always in laboratory scale. The laboratory scale, it is not possible to use always fresh bone samples taken out of dead bodies. Okay, because there are various ethical issues related to that. I myself performed experiments long time back when I was a PhD student in Delft, but those, during those times there was it was not so strict. Okay, in the last 15-20 years, things have become very difficult. Various ethical issues, legal issues are involved in testing fresh cadaveric samples. Okay, so this composite bones, sawbone, it comes from sawbone. You can check the website also. It is very expensive actually. I had shown you sawbones. I have it here at home as well. Just a moment. Exactly this bone. Okay, this is exactly the bone. It has a core, cancellous core, and an outer cortical shell. But this is very, very expensive. And these are used for experiments as well. Okay, so pelvic bone samples are also there. So let me check in my bag. Yeah, I do have it. I brought it from my office to show you. This is the composite bone structure. Okay, but remember, every millimeter is designed. It's a representative bone structure that can be used for experiments. So you have a polyurethane internal structure of cancellous bone and a glass fiber reinforced sort of a cortical shell, cortical bone. But we have performed experiment on this and we have generated the model exactly on this geometry, CT scan geometry.
Sir, how do we generate the 3D model using the 2D CT scans? Because those CT scan must be one direction only, right?
No,
And
it is
with
2D.
this much of
Not
detailing.
one direction. It is, it is a slice. Okay. So suppose you look at this spectacle case, for instance. If you do a CT scan, you get slices one after the other, right? And if it is very
Yes.
closely spaced slices, you can fit a surface over it. Of course, there would be little errors depending on the complexity of the 3D geometry. Okay, but this is a layer reconstruction method. So you can actually have closely packed layered stack over each other contours, which are generally 2D. Okay, so and then you fit a surface over these contours, right? You basically skin a surface. You remember the Pappus theorem?
No, sir.
You remember that you revolve if you rotate a line, so you rotate a line through angle, you get an area. You drag an area through a distance, you get a volume. But here you have to fit a surface. You have to fit a surface, say somewhat like here. It's complex because it's curved. A straight surface, but it's curved on these two sides as well, anterior, posterior, superior, inferior. Okay, so you have to fit it through using those contour lines. You can skin a surface. It's like a covering. That's a mathematical procedure.
Yes, sir.
I will tell you later on where are these, there are errors in discretization. So discretization errors connected with regarding this 3D reconstruction. Okay, so if you have, I'm very quickly saying this because we have a little bit of time. I will continue maybe in the next class, the other on optimization. It's very interesting. The next lecture, not next lecture, just few slides on, if I go through this shape optimization of the prosthesis by another PhD student who is now a faculty at IIT Guwahati. Okay. This is also very interesting, highly mathematical and computer intensive. But before that, let me tell you, see, if this is the boundary of the bone, I'm giving you a simple example. And if you are doing a CT scan, at this curved area, when you are sort of fitting the surface, you can end up generating the geometry, the fitted surface outside, very easily outside the bone boundary. Isn't it? Am I clear?
Yes, sir.
Is everybody listening? Just try to be careful. It is in the online mode, you can easily lose concentration. So when you fit a surface in complex region, curved regions, you can end up actually with a surface generated beyond the boundaries of the contour. Okay? Then when you are actually trying, and subsequently you generate finite elements, and when we try to pick the CT gray value, when you place the finite element back to the CT scan data, there you can easily make mistakes because these elements would be actually generated outside the bone contours. And immediately you get very low values of CT numbers there. Because it is already, soft tissue or fat or water, something, you get close to zero values. So what happens, you have to be extremely careful. This is called a partial volume effect. So partial volume actually is located in no man's land, and you can actually make mistakes by picking up erroneous CT gray value, and which will influence your E modulus. We have seen that. How to rectify that? You generate an outside, a very thin layer, say 0.5 millimeter, maybe 0.8 millimeter, an outside segmented layer of cortical bone. And then you force with a value. Okay? So now you get rid of this partial volume effect, that you don't end up anything beyond the boundaries of the CT scan. And inside, you base all the data on your pure CT scan, and it will never get errors due to partial volume effect. Is it clear?
Yes, sir.
So in order to get rid of this partial volume effect, see, it is a reconstruction. Okay, reconstruction, depending on the complexity of the geometry, the reconstructed geometry will always have a little bit of errors towards the surface fitting and near the boundary. So we take care of this error by doing some improvisation. Okay, and that is known as how to correct partial volume effect, which is an inherent error. And you will get complete erroneous stress strain distribution, because if you have a low value of E modulus, immediately it will show up in your stress analysis. You will have very high strains on the surface, isn't it? And low stress on the surface, which will never give you true values. Okay?
Yes, sir.
So you have to always question your model. You need to question your model so that you can get rid of discretization errors like this. But as you see, we have compared using these sort of detailed techniques and being critical to our own generated models. We finally ended up with excellent results when we compare predicted values with measured values. Okay? Clear?
Yes, sir.
I think we have to end the lecture. 1 minute to go. Okay? Let's meet tomorrow. Boys and girls?
Yes, sir. Thank you, sir.
Okay. I will, by the way, I will tonight upload this lecture as well so that you can start following it. Okay. I will also upload the PhD thesis of Harry Winans. Okay. Who is sort of it's a very old thesis, a Dutch thesis. So it's in the form of a book, but you can also get details. But it is always better. I never did it earlier, but if you people seem to be very much interested. I like your keen interest in the subject. I will upload it for your convenience. But if you read the Biomech 1 doc, Biomech Doc 1 and Biomech Doc 2, those things are actually introduction to 2 theses, and you can get a very comprehensive idea of the whole subject. You had you have studied a part of it connected to your musculoskeletal system. Now, if you move to the bone mechanical properties, implants, failures, bone remodeling, state-of-the-art problems, everything is written there in a very short but objective manner. Okay? Thank you.
Thank you, sir.
Thank you.